All right, welcome everyone. I'm glad that you are all here to hear a presentation by our very special guest, Professor Morton O'Kelly. He flew to us here from Columbus, Ohio. Originally, Morton O'Kelly earned his bachelor's degree from University College Dublin, and then later earned his master's degree and PhD degree from McMaster University in Hamilton, Ontario. After graduation, he moved to Columbus, Ohio for a tenure-track position at The Ohio State University, where he has spent his entire career. Of course, he became full professor there, and he also served 10 years as chairperson and dean of the college. But currently, he is emeritus professor in the Department of Geography at The Ohio State University. Throughout his career, he has advised a total of 28 doctoral students, and it is a privilege and honor for myself to count among those 28 students. So yes, in fact, Dr. O'Kelly is my advisor for my master's degree and my PhD. A bit about his research activities. So Morton O'Kelly has spent his entire career on topics related to spatial interaction. And so hence the topic of today's talk. Two main areas of current research. One is hub network design, especially in connection with cost and environmental impacts. And two, many aspects of spatial interaction for commuting. His work spans quantitative social research, economic geography, and transport economics. His areas of expertise include spatial analysis and location theory. He is author of over 115 papers and continues to pursue research related to geographical analysis, optimization, and transportation. His work has been funded by the United States National Science Foundation. And looking over his CV, I counted 6 NSF grants. In 2017, he received a Lifetime Achievement Award from Informs for contributions to locational analysis. So it is my pleasure to introduce you to Professor Morton O'Kelly, who will give a presentation for us today.
Thank you very much. It's a great honor to be here. Thank you for the invitation to come to speak. Thank you for permitting me to speak in English. And it's also wonderful to visit an institute where the term spatial organization is part of the title, because that's something that's very important to me and to the work that I've done. So thank you again very much for the invitation. It's an honor to be here. I want to talk a little bit about, spatial interaction, which is a very strong aspect of geographical analysis. I want to jump right into the talk. So we all know that spatial interaction is a very important part of what we do. It includes push factors, pull factors, and it has been revolutionized by the availability of large data sets, and that's partially what I want to speak about today. So I've done work on modeling for many, many years, but only recently have we had a great development of wonderful data sets that are far bigger and more detailed than we ever could have imagined. And that helps us to look at some special and unique and I think interesting new features of geographical analysis. I also want to hit on a theme that has been part of my work, which is to always ask the question about transport efficiency. So transport is, as you know, a burden. It's almost a waste of time, but we have to do it to move material or people or resources. So how can we make sure to try to do that in a way that is good in comparison to some benchmark? So if I tell you a standard, can we see if our system is doing well compared to that benchmark? And in some ways we want to see, are we being wasteful? Or is there a waste of transportation that we could improve? So now all of the types of interaction I want to talk about today, 3 of them, bikes, the commuter bikes, commuting traffic, and airline transportation, I want to see if there's some general purpose results and tools that we can bring to all of these different areas. Now, don't make a mistake here. We're not going to make the error of thinking that one model will fit everything. Absolutely not. There's no effort to make a general model, but there is an effort to look for similarities in processes. The same fundamental ideas might have a particular importance, whether it's for air transport, for commuting, for bicycles, but of course each one will have unique and special features. So I think in the early days of spatial interaction modeling, way back maybe 40 years ago, people might have had the grand idea that we can get laws or general theories that would be applicable to everything. I don't think that's necessary. We can instead look at rich data sources that will give us details about the particular transport mode that we're examining and make adjustments that are appropriate for each of those different types. So here's the kind of the plan for what we might do in this talk. We want to look at an interaction system. We know that it takes effort to make interaction. You travel, you drive, you walk, you take the airplane. But how good is that compared to, say, the minimum cost, to an average cost? How are we doing is essentially the question. How is our transport system operating? And I've been extremely impressed visiting Warsaw for the first time to see how great your system of public transport is. You have wonderful, I think, wonderful ways to connect people by efficient means. And I come from a city, Mike will tell you that we have terrible buses, and you guys have trams and metro and bus in a way that I think probably means you're being efficient and likely quite energy efficient as well. I'd like to talk about maps. So in spatial organization, we are interested in mapping. We'd like to look at models to see if we can have a mathematical representation of the data. So maps and models are, in a way, the building blocks of spatial organization, the building blocks that we use repeatedly. I'd like to look at a sort of a repeating theme is the idea of average trips. So I make a trip, you make a trip, you all make trips, we could take an average. How is that average in comparison to other people's experience? Are we particularly lucky and we have a short trip, or are we on the periphery and have a long trip? And so the difference between contrasting core areas, which I think have beneficial access, and periphery, which is a concept meaning like the edge, it's obvious that there's going to be a contrast between the levels of transport provision and availability and access for both those regions. I think those themes are very important for, I would say, for Polish transportation, because I've heard talking about, people who have less good access or somehow at the edge. So I think I really want to stress and show you examples of how core areas can have advantage and peripheral areas are disadvantaged. Now, those ideas are not new. They're basic building blocks of our entire literature. But with new big data, we can perhaps find a better picture of those. We can find a much nicer illustration of those concepts than we could in the past. So fundamental to transportation movement is the idea of a flow between an origin and a destination. So we have origins and destinations. We have flows that occur between them. Interaction takes place between those locations. And this can be passengers, information, material, resources, with supplies. And so the flows take place between origins and destinations. And often in the network, those flows are channeled, in English we say, between hubs. So a hub is going to take the flow from one region and amalgamate it into a central point and then send it off to its destination. So I flew here through Paris. Paris is a hub in the Air France system, as you know. London Heathrow for British Airways, et cetera. So here's the three examples I wanted to talk about. City Bike is a bike sharing system in New York. It's very large. And I notice you have a bike share system too, and I think you'll be interested to see some of the features of the City Bike system. It is a system that generates at least 3 million trips per month. So it's big data. There's a lot of people use this bike system because it's very important. Second big example might be Shanghai, which is a big city in China, which has tens of millions of movements and interactions. So again, a very large data set. And then not quite so big, but Scandinavian Airlines is a system of flows between places. So bikes, cities, and airlines all give us an example of somewhat large data sets that we don't have to have like paper books to look at the data. They're all digital databases that we can use and link to our mapping and to our analysis and our spatial models. Every one of these three examples has some particular issues. In the case of bikes, we might want to map accessibility. In the case of commuting, we might like to look at the importance of income or education or social differences in the level of commuting. And in the case of an airline, we might like to look at the special role of hubs. So Copenhagen in Scandinavian airline has extremely high connection to lots and lots of different places. And how's that different, say, from Warsaw? So we will look at some of the differences between connectivity. And then finally, all of these three areas give us an opportunity to ask questions about wasteful transportation or excess movement. I would say that in a bike system, it's less likely to be wasteful because human effort is needed. People have to actually cycle, so they're not going to, probably not going to waste time necessarily. But commuting, people definitely in some cases commute in excess of the minimum, especially if they have a car and they have income and they have a high prestige job. They may decide to live in a nice suburb and commute 15, 20 kilometers to work instead of living very close by. And of course, in airlines, you might wish to fly to Oslo tomorrow, but you might have to travel through some intermediate stops because of the way the airline is connected. So these are I want to talk about the bike system first. So the bike system in New York, I was able to live in New York for 6 months. And while I was there, I spent the time studying the bikes because you start to notice examples. And I was able to gain access to the data for the bike system. It's public available, and it gives you a measurement of how people are using the bike system. Bikes, I think, they're healthy. They're environmentally friendly. I think in a city like yours with bike lanes, they can be safe. And in many cases, the bike system provides a complement which allows you to link into other locations. So let's look at that a little bit. So the bikes in New York, these are the number of users in the month of June in 21, 3 million, and in June of 22, more than 3.3 million. So that's 1 month's worth of movement in the bike system. On average, their trip time was this, not too much change. And the interesting thing, I think, I'll just go to the bottom line here. This is a very large system. There's over 1,500 bike stations. So this gets the advantage of what economists call network effects. When you have lots of stations, then there's lots of things you can do. If you only have 2 or 3 stations, you have a very small number of choices. But with 1,500 stations, you have a huge array of potential linkages. So I'd like to show you a picture here. This is in an area of New York called Greenpoint, which is actually a Polish neighborhood of New York. And it's the same picture. The tree is the same, here and here. But the bike on the left, almost all the bikes are gone. And the bikes on the right, they're all full. So that's a feature of the bike system. The bikes flow. They fill up, they empty, they fill up, they empty. And so systems are very dynamic. And the database will tell you when the bike left, where it went to, and how it accumulated or depleted at each of the stations. So the individual, let's say I go to the station, I want a bike, I click my card, get my bike, and I cycle to the other station. That constitutes one trip for me. And the trip can be marked by its departure and its arrival. So I think you have the same system. But the interesting things about looking at big data for a system like this, in spatial interaction terms, is that we can begin to notice some unusual things or special things that are worth talking about. First of all, bikes, in a somewhat unusual way, often have what are called a loop. So I take the bike from Greenpoint, I cycle for a half an hour, and I come back to Greenpoint. So in that sense, I'm like a tourist. I take the bike for fun, or I take it for a leisure trip. Other people take the bike at Greenpoint and say, I want to go to the subway station. So they have a purpose that's to do with commuting. Some people are members of the system and they have a card and they just click and go. And they're quite different from casual users who just come and pay for the one-day trip. So the casual users and members have quite different usage patterns. So with this great amount of data, we were able to look at which stations accumulate bikes, which stations lose bikes, where are people going, which ones are interesting. So this is a very, maybe potentially confusing map until I tell you the code here. The big red dots are subway stations on the metro system, train stations. And the brown lines are cases where, let's take this subway station here. All of these bike stations had their biggest flow to that metro station. So in a sense, the bikes are serving as an extension of the metro system, allowing you to reach beyond where the end of the subway line is. And you can particularly see that up here. This is a subway stop at the end of a subway line. So clearly, if I live 2 miles or 3 miles or 4 kilometers beyond that point, I need some way to get to the subway station. So we found that a very strong organizing principle for bringing some organization to the chaos that this system looks like. One key thing is the way that the system is interconnected. So multimodal flows between types of interaction is a good explanatory variable in this case. More interesting is that the bike system in New York is actually owned by Lyft. You know that company, L-Y-F-T? It's the car share company. So the car share company is also providing this kind of transport service. And I think the way that we're going in terms of mobility as a service is to have someone with a card, and that card gives you access to trains, to buses, to bikes, to ferry boats, to taxis, everything, even rental cars are all on the same system. We also would like to look at, this is a little bit harder to understand, but here's Manhattan Island here, and here we have Brooklyn and Queens. These are the boroughs in the outer areas. So the difference between yellow and blue. Yellow here are areas where the majority of the users are casual. They're not members. So it could be that this is, the service has recently been introduced to a new region and they're beginning to get used to it and they're becoming users. And the dark blue are members of the system. The trip length, so trip length here, as I'm beginning to get into my discussion of core and periphery, in a core area, you'd expect trip length to be short. You have close access to a lot of things. So the yellow are the shortest trip lengths. So they're short in the financial district of Manhattan. They're short in the core parts of Queens and Brooklyn. And as you get to the edge, this is peripheral. Obviously, the dark blue is a longer trip, and they have less advantage in terms of access to the system. So a very interesting aspect of bikes, which I can only touch on today, and I suggest that if you look into this, you'll realize that some very smart people have worked very hard on this problem. And that is that bikes are either filling up or emptying out from a station. There's an asymmetry. So a full station with lots of bikes, but there's no place for you to dock your bike. So there's no gap. An empty station, you can dock your bike, but you can't get a bike. So there's an asymmetry. So here's 2 pictures to suggest examples. This was taken outside a park in New York. And as you can see, the station, as you glance at it, is virtually full. Every dock is taken. So there's no place to put your bike. So what stations look like this? Here are a map. Here, this is a map of stations that tend to look like that one I just showed you, that they fill up. They fill up in Manhattan, and they fill up a little bit harder to understand, but they fill up near ferry points or near metro points. So there's stations that are inclined to fill up, and then in contrast, this is a very sharp contrast, an empty station. This is a bike station where there's no bikes. Where does this happen? Well, it happens all over again, but particularly it happens in here around Central Park, where people may take bikes for fun and go for a pleasure trip, and they empty the stations out. So that gives you a visual picture of blue stations that fill up and red stations that empty out. So mathematical model, we want to look at a time. Time is going this way. And at one particular time, there are red stations and blue stations, stations that are empty and full. So mathematical model, we want to have a constraint that says, take care of the need for bikes at the red stations and remove bikes from the blue stations, meaning we have an available supply and demand pattern that we wish to balance by movement of bikes. So this is what we look. We have a bike deficit. You know, this word means like an absence of bikes. And so that's a place to which we want to sink new bikes into. That's a red constraint, like this one. And a blue constraint, we have too many bikes, we need to take them away. Now, that model is very simple. It's a linear program. If we are careful about our flows, it will move the bikes correctly. But the reason this problem becomes so much more complicated is that we need also to do vehicle routing to take the bikes from one station to the other. We need to have a capacitated vehicle routing. And when I talk about wasting energy in transportation, you can obviously do this very badly, or you can do it very well. And the companies have spent a great deal of time trying to figure out how to do it very well, i.e. avoiding waste. So avoiding waste in redistribution is kind of a key problem. And I don't want to do more than that today, other than if you're interested, there's some tremendously good operations research work that shows how to potentially optimize this and develop a plan for movement of bikes. It would be interesting in the case of Warsaw to see whether you have a bike balancing problem. I suspect that there are some stations where there's too many and some with too few, and maybe that can be corrected with just one quick sweep of a truck that will move the bikes around, but it could be more complicated, especially when the system gets bigger. That's kind of the end of one little chapter here of what I wanted to talk about. The second thing I want to talk about is a quick methodological detour, which means I said to Mike, could I do a few minutes on showing you an example? And so that'd be good. And so what I want to talk about is a difference between origin-based average trips and destination-based average trips. So an origin is I'm sitting here at my origin home, and I'm interested in where can I go to and how far should I travel? That's origin. And on the destination end, you know, take an office building and say, where did all those people come from? What was their average experience? So in this picture, the origin is in the middle, and I look out and I say, where can I go and how far do I travel? So these four lines here are telling me the flows from this station or from this airport or from this city. This is the flows from those four. And we can measure, you know, the distance of those flows, the weight of those flows, et cetera, et cetera. That's easy, I think, right? A little bit more tricky to get your head around is this case here. So given that we're heading to destination one, what do other people who come to destination one experience? What is their flow pattern? So this is the incoming destination flow, I'll call it CD, to destination one. The incoming destination flow to 4, the incoming flow to 3, and so on. So my origin has an experience, and the destinations I go to have an experience. And it's the contrast between those two numbers that I want to explain. Okay? So little spreadsheet. Here's an interaction table, TIJ. Here's a cost table, like transport costs. And it's very easy to see we could take the average by weighting that row. You see that row 1, 2, 3? We can weight it by these proportions and we can get an average. So this is C0, the outgoing trip length from origin 1. The outgoing trip length from origin 1 is like this number here. Okay with that? I think that's the very easy one. The one that people don't think about is the incoming trip length to, say, destination 3. So here's destination 3. All these trips come into 3. Therefore, they have these weights. They have these distances. And when we put them all together, we get 1.45. So that's this one. Okay, so now we got two numbers. We've got my origin trip length and my average incoming trip length. What I want to do is compare the one I call the easy one, the incoming trip, the outgoing trip length 1.8. Well, I want to compare it to this number here. What is that number? This is the hard part. We want to average from origin I's point of view the trip lengths of all its destinations. So of all the places around that we're going to, let's average what all of those guys have as their trip length. And that number is 1.76, right here. Now, promise this is the last complicated slide. Here's the difference that I want to talk a lot about in this paper. The difference between C0 and that second number I talked about. The first number I said is the easy number, 1.83. That's an easy number, the average of where I went to. Then the average of the other people coming to the same places was the harder one to calculate. And in this case, the difference between these two is positive, which I colored pink. And in the second case, the difference between these two is negative, and I called it advantage. So that's easy to get. If I'm lucky enough to have a trip length of only 1.5, and all my neighbors have to go 1.6, I'm better by that much. So if we map the pattern of accessible and inaccessible origins and destinations, we ought to be able to show a contrast between, I think you would agree, the core areas will have the advantage case, and the peripheral areas will have the disadvantage case, because they'll have to go further to get where other people can get cheaply. Okay, so the core and periphery, when C0 is greater than this, the origin needs to travel further than the typical distance. Such access is not so good, and we will call it peripheral. So positive values of this difference will be case 1, and they're periphery. And negative values of this difference are core, and they're advantageous. So we're going to look at this for bikes. Which parts of the city have good bike access and which have poor bike access? So I shared this talk with Mike, and he mentioned this slide is very hard to understand, and I agree with him. So instead of showing you this slide, I'm going to show you, just focus in on one of them, okay? We can do lots of different maps, but let's just pick one. So here's a map which shows the pattern of C0 minus TD, CD, and it's colored red and blue again. So when it's red, we are in the lucky position that our trip length is short and your guy's trip length is long. So in a way, this bike station can get places very easily. That happens where? It happens in the red zones, and they're almost all at the core of these boroughs. So the city is made up of different boroughs and subdivisions. So this is the core part of this area, this is the core part of this area, core part of this area. So it looks like a mess, but each area has its own bullseye where the core access is central in the main part. And the blue, as you might think, are the opposite cases. These are the disadvantaged cases where they have to travel a long ways compared to what other people can do, okay? And so this would be, the blue would be unfavorable, the red would be favorable. I think that's pretty clear. So we have a lot of maps that show this for the system in New York. And this illustrates my point that maybe 50, well, I won't say 50 years ago, 10 years ago, we could certainly think about access and we could think about mapping core and periphery, but we didn't have big data that would say, show me the actual experience that underlies the routine mapping of core and periphery. I think that's a core concept. And what I used today was the bike example as a quick way to kind of get a good feel for that, because you can all appreciate the bike transportation. But the same measurement is going to be used for commuting, for air transport, or whatever. So that's my point, where we don't want one model that fits everything, but we have one conceptual technique that makes sense for different cases with appropriate modifications and changes. Okay, I'm going to switch to commuting now, and we have questions on this later if you would like. So in commuting, and Mike and I have done quite a bit of work on this, commuting essentially has the same question: where am I going to drive to work, or take the bus, or bike to work? And what about other people who go to the same place? Do they have the same experience or worse? And I'll skip this one to this picture again, blue and red again. So if you have a pattern of jobs which are blue and housing which is red, it could be that everybody is kind of matched exactly with their nearest job, and everybody is going very small distance to work. Well, cool. It's a minimal theoretical situation. On the second case, there might be a little bit more mixing up than just the minimum case, but a little bit more interconnection. Even worse would be if people commuted randomly, which they don't. Or really worse would be if people commuted counterintuitively. They went as far as possible. Nobody does that. So this is the minimum, where the benchmark is as small as possible, the observed pattern, random pattern, and absolute wasteful pattern. So where are we on that spectrum when we look at cities? And you can see how it's the same sort of questions we had with bikes. How much are you spending to do your movement compared to, say, a benchmark or a standard? And how much excess is being spent on that? So this is where there's a little bit of a theoretical disconnect in the paper, because we have to, I'll provide some reprints if you'd like. But in the commuting measure, just like we took CD minus CO, that difference, in the commuting measure, we have a series of papers that measure these two things, DL and DM. It's like the difference in the values that we spoke about. And it turns out that those measurements can give us a good clue about spatial organization. Which zones of the city have sort of wasteful commuting, and which zones of the city have not so wasteful commuting. And if you're going to work at a factory or an office, your wage has to be enough to cover your rent and your travel costs. There has to be enough in your budget to cover all of those costs. So Shanghai is a very, very large city, and my co-author, Li Ying Yu, and I have begun to look at commuting trips in Shanghai. And I think everyone would agree this map is extremely hard to understand. It's a mess, right? It's too much. So one thing about mapping spatial organization is to zoom in on the key, most important parts. What are the significant parts, and wash away all the detail. So if we boil this down to the really major trips, one key important feature of Shanghai is the very strong, purple means inflow, strong inflow to workplaces at the city center, and particularly strong inflow to these workplaces here to the east of the city center. And I've not traveled to Shanghai, but I can tell you that these include the business called Huawei, which is the big telephone manufacturer, and essentially is a science research park. And it's a very attractive, high skill, high income, high prestige place to work. And if you work there, you may commute from maybe further away. Whereas if you work maybe in a service job in another community, you might walk or bike or take a bus to the local community. So what we have shown, and this map is only a partial picture, is that some of the communities are what we call self-contained. They have good jobs, housing balance. People live and work in the same area, like these. Some involve a lot of leakage and flow in and out. And we wanted to, if you think about it, the planning literature has really made jobs, housing balance a good thing, a gold standard. We want balance between housing and jobs. But the price of doing that is to have people having very constrained spatial worlds, so they live and work in the same village or town or area. And as you give people higher income, higher prestige, a car, and education, they are not going to be happy with that. They're going to move much further in terms of their commuting patterns. So our prediction is that as Chinese cities become more wealthy and westernized, and they are already there in terms of car ownership and income, all the good things they had about people walking and biking and taking the bus to work are going to go away. We're going to have much, much, much more congestion and commuting. That was a brief example. I can provide more detail on that. We have a series of papers that are currently under review on that. But in view of the time, I'd like to go quickly to the third example, which is a similar case, which is to look at aviation. So again, we have flows. We have the airlines, Scandinavian Airlines. I know they have some trouble, so we will look aside from that. But Scandinavian Airlines is a big airline. And look at the thing I have right here, CO minus TD CD. This core computation of difference between how far you travel and how far other people travel to the same places you travel. So if DL is positive, we have a distance that's larger than those of the destination. We are in a disadvantageous position. If DL is short, we are in an advantageous situation. So again, the contrast between the benefited core locations and the disadvantaged peripheral locations will be very sharp in this particular case. The one thing I want to explain quickly about transport costs in this model, I'm going to use hops. So if you travel to Copenhagen, that's one hop. If you travel on to London, that's a second hop. And to New York, that's 3. So not exactly distances or fare, just hops. But it's a quick way to measure distance. So the same picture we had before, we're in the middle. How far are we traveling compared to how far other people are traveling to the same places? That's a core concept. So this map here, it's not drawn in a geographical way, it's drawn topologically. So Warsaw and Copenhagen and Dublin are not in the right positions, but they're in the right network positions. So Warsaw is connected by a link to Copenhagen, Gdansk to Copenhagen. Dublin is connected by 2 links to Copenhagen and Arnhem. So cities that have a link to a single hub are shown up here and around the edge. Cities that have links to 2 hubs are shown here and here and here. And cities in the middle that are connected to all the hubs are in the middle with 3 connections. So, for example, we don't agree that Zurich is a very important city that's connected to Oslo, to Copenhagen, and Arnhem directly in this network. So they have a lucky situation there. They can get everywhere with only 1 hop, or 2 hops perhaps. So Zurich is going to be advantageously located in this system. And Warsaw, not so good, because to get anywhere in this airline, of course, not other airlines, but in this particular airline, you would have to go first by linking and make multiple stops. So if we color the nodes by green is positive DL, which means you have a bad location. So Warsaw, sorry, the color is washed out, but Warsaw is green, Gdansk is green, but Zurich is orange because it's advantageously located. So this is a key situation where we can measure the same concept with big data. We don't have exactly the same model, but we have the same conceptual overview. So in about 5 more minutes, let me wrap up some of the key ideas to do with air transport situation. So I think this is a useful idea. Every airline is going to be able to carry you to your destination. Okay, they're going to take you to your destination. They may make you change. Like when I flew here, I had to go to New York, to Paris, to Warsaw. So hop, hop, hop. If you're going to Copenhagen tomorrow, you can fly direct, I think. So think about the division of connections, the OD connections, into three types: direct, one stop, and two stop. That's all we'll talk about. And you might say to yourself, I want to go on an airline tomorrow to London, and there's a direct flight. I love that. I'm going to fly direct. But amazingly, even when there are direct flights, people often use one stop on that particular route. Why? Well, maybe capacity, the direct flight is full, or it's expensive, or it doesn't go at the right time. So one of the advantages of a hub and spoke system is that it gives you a greater multiplicity of connections, many different ways to make connections. So one of the things that when we look at airlines, big data, airlines, interaction, same concepts, mapping to try to pick out the major flows, what we want to do is look at the fraction of flow on each of three different types. The fraction on direct, one hop, and two hop. And if you think about it, the sum of those three values is 1. You're either going to go direct, one stop, or two. So this type of information is perfect for plotting on what's called a ternary diagram. And I'm very pleased with this kind of picture. I think it shows us something very, very interesting. So a ternary diagram, it takes a little bit of a minute to guess what's going on here. There's three axes. And if I start at this corner right here, this is where everybody's going by two stops. And then the percentage by two stops is dropping, 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 dropping. And on this edge, nobody's going by two stops. Right? So everybody two stop, nobody two stop. So that means these guys are going by 0 or 1. Right? They don't have that as a choice, so they're going by 0 or 1. And you would say, like I said a minute ago, if you have 0 as a choice, why would you ever go by one or more stops? But in fact, in Scandinavian Airlines, there's lots of trips that, even though they have a direct connection, are using a one-stop trip. Similarly, let's go another direction. The top of the triangle is direct, 100%. And 100 direct is getting less and less and less and less and less. When you get to this edge, direct is 0. So that means it's either all 1 or 2. So 1 or 2, you might say, well, I have a choice between 1 or 2. I'm always going to go 1. But in fact, again, there's a mixture of 1 and 2 stops. So what we find is in an airline that provides trip options, it provides an interesting range of choices, and the consumer will base it on time of day, price, capacity, convenience, etc., in making their choice. I would love to see this for LOT or for Lufthansa or for British Airways, which would be quite a bit more complicated. I think British Airways is going to have a much more stuff in the middle. SAS, Scandinavian Airlines, is particularly hub-oriented, so the edges are very, very important. The 1 versus 2, 0 versus 1. Nobody is 0 versus 2. That makes sense. Okay, I'll stop on the next maybe 2 cases here. So the case 1 is where direct and one stops are possible. That's the outside edge. These are pairs where there's no presence of direct service, and this is the lower edge. Now you might ask yourself, I'm Scandinavian Airlines, how much of my effort as an airline is spent transporting people on types 1, 2, and 3? Obviously, if I'm type direct, I'm just going to get on the plane, fly to Copenhagen, and we're done. No waste, right? If I fly via one intermediate stop, I'm clearly going to go more miles, and there's, in a sense, more lift needed. So I have, this is my second last slide. So the passengers who flew on a direct link was 17 million, and that's 54% of all their traffic. The passengers who flew with one stop is 12 million, but that accounts now, of course, for 24 million stops because they got to go two per each, And then the third one has 2 stops, so it's a smaller number, 2 million, but that accounts for 6 million stops because they go twice. So of all the traffic, 54% is direct, but of all the lift, 50% happens on the one-stop trips. So it's a way of showing that the effort needed to move passengers in the transport system can vary by the type of flight. And I'll just show you one summary slide then to wrap up what I've talked about today, and thank you for your attention. First of all, we've used big data, 3 different types of big data. We've used diverse examples, including commuting, air, and bike. I think there's some core ideas. No one's pretending to get a unified model for everything, but there's fundamental concepts of accessibility, core, periphery, hub. Those ideas are very useful and underlie all 3 of these cases. And I think maps are very useful, as you saw a variety of maps in the talk. And I think there's much, I hope this talk maybe will inspire some opportunity to look at extensions of these ideas to some new data, either from European or for global opportunities. So thanks for your attention, and I welcome any questions that you might have.